These notes are for Calc AB on 6.4, which is on properties of definite integrals. So in this objective, we're just going to talk about all the ways we can manipulate integrals, whether we're working with one function or two functions like f and g. So we'll see that later down here. Our first example, or our first property, says that if the function is defined at any value, then the integral from that value to itself of that function is just 0. So that's because our width here is 0, so the area itself would then come out to 0 as well. If f is integrable on a closed interval ab, then the integral from a to b of that function, I can actually swap the values around, and what happens, it becomes negative. If it starts off as negative, then you just add in the next negative and it becomes positive. The third property says if f is integrable on 3 closed intervals, so a to c, c to b, and a to b, so determined by a, b, and c, then we have the integral from a to b, which is the entire interval here, is equal to the sum of the two parts. And so I've colored it here so you can see that. So adding the area of the region bound between A and C to the area of the region bound between C and B gives us the total area bound between A and B. The last one, or last two in here, tell us that if I have two functions that are integrable on AB, and if I have a constant k, then the functions k times f and f plus g or f minus g are all integrable also on the closed interval AB. And the following can happen. So in the first one here, we have a constant that is removed. So any constant can be taken out of the integral. And I can split up the values inside of my integral into two separate integrals. And really, we've been kind of doing this anyway, especially all throughout Unit 5 when we were just evaluating indefinite integrals and we were just integrating each piece individually. That's basically what we were doing here. It just shows that it still works on a defined closed interval. So we'll be using these 5 properties for the next few examples. So below here, you've got 2 examples. The first one defines x squared from 1 to 3 is 9. The integral from 1 to 3 of x is 4. And the value of the integral from 1 to 3 of 1 is 2. So with that, we want to evaluate the following things. So first, the integral from 3 to 1 of x squared. So here, the values are switched, and they need to be in the order 1 to 3. So remember, bottom to top, A to B is 1 to 3. If I switch them around, I'm using that second property that says if I switch the values around, we end up multiplying by a negative, x squared dx. Then we just make the substitution. The integral from 1 to 3 of x squared is equal to 9. So this is now negative 9. For part B, evaluate the integral from 1 to 1 of x dx. So this isn't something that was defined or given in the problem above, but because the values here are the same, 1 and 1, this is using that very first property that I introduced to you, and so it has a value of 0. For part C, we're going to take 12, which is our constant, out of the integral. So this becomes 12 times the integral from 1 to 3 of x dx. We can then make the substitution. 1 to 3 of x dx is 4, and we're left with 12 times 4, or 48. For this last one, we're going to need to separate our terms individually. So we're going to break it up using the last property here so that I can evaluate each term separately. So we'll have 1 to 3 of x squared minus 2, the integral 1 to 3 of x, plus, we'll just go ahead and leave this as 1 to 3 of, oh, we're going to take out 3 so that we have a 1, so plus 3, 1 dx. So I went ahead and did both properties at the same time. So as I was splitting it up, I took out any constants so that I leave behind x squared, x, and 1, so I can make my substitutions. So now the first one, we'll just substitute with 9 minus 2 times, the second one has the value 4, plus 3 times, the last one has a value of 2. So 9 minus 8 is 1, plus 6 is 7. All right, so number 2 is a different kind of example with different given values. This has negative 3 to 0 of f of x and 0 to 2 of f of x. So it's the same function, but different intervals. Whereas last time I had the same interval with different functions. So it's just a matter of using maybe some different properties that I gave you above. So for A, we have the integral from negative 3 to 2 of f of x dx. So we need to remember that this, for the same function from negative 3 to 0, picks up 0 and ends at 2. So that's going to give me my total interval. So this is that third property. So negative 3 to 0, and then continue from 0 on to 2. So if I add the 2 together, I get that full interval. Okay, so that's what this is here. So we're going to split it into negative 3 to 0, f of x dx, plus 0 to 2, f of x dx. And so the first one has a value of 4, the second a value of negative 1, and so we get 3. In part B, evaluate 2 to 0 of f of x dx. So 2 to 0 is just backwards of what we want, which is 0 to 2. So if I want to flip my values around and make them 0 to 2, we're just going to multiply by a negative, f of x dx. And now I can substitute 0 to 2 has a value of negative 1. So the opposite of negative 1 is 1. In part C, we want to evaluate negative 3 to 0 of f of x plus 6. So what we want to do here is separate the functions. This is f of x, which is the function I was given information about. 6 is a constant. So anytime I'm given a constant, I can always deal with that on its own. So I'm going to use that last property and split the 2 up. Same interval, negative 3 to 0 of f, negative 3 to 0 of 6. So that's what the property has there. Now, the first one has a value that I was given, which is 4. The second one is a constant, and we remember that as long as my function is non-negative, then my integral represents area. The area is always width times height. The width is the interval width, negative 3 to 0, so that's a width of 3. And then the height is my constant, which is 6. So the area of this space, which is just a rectangle, is 3 times 6, or 18. 4 plus 18 is 22, and that is our answer. And then we have one more type of problem that we're going to do. So number 3, with some different given information. So here I have two functions on the same interval. So f from -1 to 4 and g from -1 to 4, and their defined values. So here we're going to evaluate first -1 to 4 of f of x minus 3 times g of x. So I want to separate my two functions, and to get g of x alone, I'll also factor out the -3. So I'm going to be using the last two properties at the same time to separate and take out any constants. So -1 to 4 of f of x dx minus 3 times the integral -1 to 4 of g of x dx. I can then make my substitutions. The first has a value of 6 minus 3 times a value of -2. So we have 6 plus 6, which is 12. In part B, we want to evaluate the integral from 4 to -1 of 25 g of x dx. So my values on my integral are in the wrong order. We want to flip them around. In flipping them around, we generate a negative 25 g of x dx. Now I want to take out the constant, so this is now -25 times the integral -1 to 4 of g of x dx. So -25 times -2 for an answer of 50. And yeah, you could pull out the coefficient 25 here with your negative at the same time, so you don't have to do that in a separate step. And this is our last example. So for part C, evaluate from 4 to -1, 3f of x plus 7g of x dx. So lots of stuff going on, separating into two separate integrals, taking out those constants, and also flipping this around. So we want to be really careful to do all of those things. And if I flip the values around, the negative would affect the entire thing. So maybe you split them up first. Maybe you start by taking 3 out of 4 to -1 of f of x dx plus 7 times the integral 4 to -1 of g of x dx. So I split them up and took out the coefficients. Then as I flip each one around, they become negative. So this is now -3 times -1 to 4 of f minus 7 times the integral -1 to 4 of g. Then we can make our substitutions from the given values. So we have -3 times 6 minus 7 times -2. And we get a final answer of -4. So I hope you understand how to use the properties that I gave to you. I think the easiest is that very first one that defined from any value to itself is always going to be 0. So keep that one in mind because besides the properties given, this one will always apply as well. And then that's going to be it for our notes on 6.4.